Okay, so in this video, we're just going to go relatively quickly through actual proofs for the quotient rule and for the power rule. Um, and uh, and if I'm going a little bit too fast, then hopefully you can pause the video and rewind it and then play it again, and then do that as many times as you need in order to sort of try to satisfy your curiosity about these proofs. So let's look at a proof for the quotient rule. I'll just do that real quick. For the quotient rule, all you really need to do is define something like log base c of a and say, hey, log base c of this particular input, I don't know what it is, but let's just call it x. And then do the same thing of a different input. So log base c of a different input b, and let's say that the output of that is y. And in each of these cases, what you're going to do is you're going to take the logarithmic form of those equations and you're going to write them in exponential form. So to write this in exponential form, it's c to the x, so c to the power of x is just equal to the input. The output of your exponential form is going to be the input of your logarithmic form, so a is going to be the output of your exponential form. And in this particular case here, we can rewrite this logarithmic form in exponential form as base c to the power y is equal to b. So here we go. We have, excuse me, we have two equivalent statements just in exponential form rather than logarithmic form. What can we do with this? Well, let's just keep working horizontally here. If we wanted to, we could divide a over b and see what happens. Maybe some relationship will pop out, and it will. If we divide a over b, that's the same thing as saying c to the x, which is just a, over c to the y, which is just b. And c to the x over c to the y is really just c to the x minus y. This is an exponent property. And we can also say that because a over b is equal to c to the x over c to the y, and because c to the x over c to the y is equal to c to the x minus y, by the transitive property, a over b should be equal to c to the x minus y. So we're going to use the transitive property to get rid of that middle and just bring c to the x minus y over here. So here, a over b is really just equal to c to the x minus y. Now, what we can do at this point is look at this in exponential form and then rewrite it back into logarithmic form. So we'll have log base c of, well, the input of your logarithm is going to be the output of your exponential form here, so a over b. It's going to be the input of your logarithmic form. The output of your logarithmic form is going to be the input of your exponential form, so x minus y goes here. And finally, what we're going to do is we're going to simply copy the left-hand side, completely unchanged. And lastly, we're just going to perform some substitutions here. So log base c of a over b is really just x. And what is x? Log base c of a. So x is really just log base c of a minus y. What is y? Well, in our original definition here, y was just log base c of b. So log base c of b. And this is our quotient rule. So hopefully this process just convinces you that the quotient rule is true. That's really the purpose of a proof, is to convince you that a relationship is true no matter what. Okay, so the quotient rule done, and the product rule we proved last time. Let's look at the power rule now. So the power rule is actually, it's not so bad to prove. So for the power rule, all you really need to do is start in a similar way. So the power rule proof and the quotient rule proof and the product rule proof can all sort of start in similar ways. We really just say log of some particular base and some particular input has some particular output. And what we do from here is we just rewrite this logarithmic equation in exponential form, so c to the x equals a. And what we're going to do at this point is we are going to raise both sides to the power n. So if we raise both sides to the power n, what we can do is we can simplify the left-hand side. This is the power of a power rule, right? So c to the x all to the power of n is really just c to the x times n. And we just have a to the n on the right-hand side. What can we do at this point? Well, at this point, we can rewrite this in logarithmic form. So let's do that. So we can say log base c of some input. What's the input? Well, the input of your logarithm is really just the output of your exponential form. So a to the n goes here. And that should be equal to, well, what is the output of your logarithm? The output of your logarithm is really the input of your exponential form. So here, and keep in mind, the input of your exponential form is x times n, and you can see here I've just written that as n times x. It's technically true because multiplication is what we call commutative. The order doesn't matter. So 2 times 3 is the same thing as 3 times 2. X times n is the same thing as n times x. So hopefully that doesn't throw you off too much. And what can we do finally here? Well, just perform one last substitution to complete the proof. We know, and we're not going to do anything to the left-hand side, as usual, as per usual with these proofs. Left-hand side just stays the same. And the right-hand side, I have this n times x. What was x? Well, x was originally defined at the very beginning as log base c of a. So here's the power rule. Hopefully it's a little bit convincing that this relationship is true. It just needs some minorly clever substitution with some rearranging from logarithmic form to exponential form, applying the same power to both sides, and then rewriting in logarithmic form, and then performing one last substitution. So what does the power rule really tell us? It really tells us that if we have log base c of some input to some power, we can simply rewrite that as log base c of that input without the power, or you could say to an exponent of 1, with the original power on that input now being like a coefficient in front of your logarithmic factor here. So, so we can essentially just write exponents on our inputs of our logarithms as coefficients out in front of our logarithms, and that will sometimes be useful. And we're going to see examples where that's useful. In general, what these rules allow us to do is to find convenient ways to expand or condense, right, to make larger or to make smaller certain logarithmic expressions. Sometimes that's going to be useful for solving logarithmic equations, which we'll do in 5.4. And in the next video, we're actually going to jump into some examples applying as many log rules as we can. So I'll see you then.